Started here. Start recording, start sharing. That way we can all be looking at the same thing at the same time. There we go. There. Welcome back. Thanks for joining us. So we have some review to do here. First off, hang on, it's blowing it up in a weird size. All right, can you all see that okay? Does that work? Big enough? Okay. So first question here, this is formative assessment number 5. In what situations would a Pearson correlation be sufficient to describe a bivariate relationship, and in what situations do you need a model instead? So what do you think, folks? What did you put down? 1. 1 is the loneliest number that you'll ever do. Do you want to elaborate on one finger?
One fixed slope.
Yeah, one fixed slope. So when is one fixed slope sufficient to describe a bivariate relationship?
When you have just one predictor.
One predictor that is either quantitative and it's a linear relationship that you're describing between the predictor and the outcome, or if the predictor is what? 2. If by 2 you mean binary, as in only 2 choices, then yes, then there's only one difference between the 2 groups and one slope is all you need. So in those cases, you could estimate a general linear model, but you don't need to, because the standardized slope that you would get out of that analysis is exactly the same thing as the Pearson correlation. The t-test for that correlation is exactly the same as the t-test for the slope, and that t-test squared would give you the f for the model, so it's all the same. But when would that process be insufficient to characterize a bivariate relationship? When do models come in handy?
There are multiple slopes or fixed slopes?
Yeah, so multiple fixed slopes for one predictor is one instance, such as if you have a linear and quadratic slope working together to describe a nonlinear relationship between a quantitative predictor and a quantitative outcome, such as if you have more than 2 groups for a categorical predictor and it takes more than one slope. So in general, it would take C minus 1 slopes for C categories. That's one instance. I can think of 2 more. One of which we haven't yet talked about, but I can think of one that we have. Okay.
The predictors are related.
Yeah, so when you have a research question about the extent to which predictors are still related after controlling for something else, the idea of unique effects too, those need to be answered in a model. Technically speaking, you could estimate semi-partial correlations for them directly outside of a context of the model, but only for bivariate relationships that can be characterized by one slope. So it's a limited way of approaching it. So yeah. And the other instance is when you want to see whether or not a bivariate relationship is different for different kinds of people. That's what we're going to start talking about today, the magic word for moderation. Okay. Anything else that you can think of for this one? Oh, I froze a bit. Am I unfrozen? Now we're okay? Okay, good. Thanks for letting me know. I can't always tell, but we'll make it work. Okay, anything else you can think of for question 1? That's what I was asking. No, we're good? Good on that? Yes? Not a rhetorical question. Are we good? Yeah? Okay, nods. Thank you. That works. R square. How do we think about R square? What does it tell us?
It's the amount of variations in the outcome variable that are explained by the amount of variation in the predictor variable.
It's not an amount, it's a proportion. But that's the right idea. It's the proportion of variance in the outcome that's been explained by the predictors. That's one way to think about it. Is R square an effect size or a significance test?
Significance test.
It's an
Effect
effect.
size.
It's an effect
Yeah,
size.
significant test would be the F.
The F that goes with it. Yep. Yep. So R square is a value that ranges from 0 to 1. It is independent of sample size, so sort of foreshadowing the next question here. And it tells you to what extent your outcome variance has been explained or captured, however you want to think about it. It also tells you something in terms of a correlation. So if I wanted to describe R square using a correlation, how would I do that?
Is there a formula to transform it into R squared, to transform the correlation into R squared?
Yeah, what is it the correlation of is the question I'm trying to get at. Because R square is a
Phone a
squared
friend.
correlation. Phone a
I'll
friend?
phone
Who would you like to phone?
whoever's willing.
Oh, that's awfully nice of you.
I can try to give it a whirl here. So I think we're looking for is predicted y hat times y sub I, or something like that.
Yeah, so not times, but y hat and y as two separate variables. So y hat is the outcome that's predicted by the model, and y is the actual outcome. If you estimate a correlation between those two and square it, that's R square. So it quantifies the amount of prediction. It's just in a squared correlation metric instead of a regular correlation metric.
Okay.
Yeah. All right, any questions on that or clarifications you want to add? All right. Oh, number 3. In what situations would you expect a unique effect of a predictor slope to differ from its bivariate effect? So unique means when the predictor is in the presence of other predictors in the same model, whereas bivariate means like if it were just by itself. When would those two lead to different answers as to its relationship?
So when a model has multiple predictors, with each of them having their own fixed slopes, then we could expect unique effects.
But when would the unique effects be different than the bivariate effects? Because you're right, but you haven't gotten the rest of it yet.
When the predictors are correlated.
There you go. Yeah. If the predictors are correlated, then after controlling for what the others have, their common variance, their multicollinearity, each of their contributions is going to be different than what it would have been bivariately. So the only instance in which you would get the same answer as to how a predictor relates to an outcome if it was by itself or paired with other predictors is if the other predictors were unrelated. And that rarely happens in outside of experimental designs in which that type of orthogonality is forced by design. Otherwise, things are usually related to each other in the real world. And here's a bonus question on that one. Is the unique effect always going to be weaker than the bivariate effect? No. A lot of the time it will be, but not always. So the way I would think about it is that the unique effect is going to differ from the bivariate effect. It may become weaker, but it could become stronger depending on the pattern of correlation between the predictors in relation to the outcome. So, good. All right, last but not least, bigger picture question. The relationship between effect size, the statistical significance of that effect against a null hypothesis of 0, and sample size. How do these things relate to each other is the question. So you all had some great answers on this one, and I have a picture pulled up to supplement them, but I want to give you first crack at it. How would you describe this to somebody? Sample size, effect size, and significance. How do these things relate to each other?
I could give it the first shot in the dark. So I think regardless, our sample size can impact both the effect size and everything, because if there's a large enough sample, then we could basically justify everything else, right?
Justify everything else?
Oh, we could basically say, oh, we can inflate or we can make a larger effect size if we do have a larger sample or not. So I think sample size will have an effect on both of those as an effect size and our significance, statistical significance. Is that incorrect or?
I would say that it's partially correct. So definitely significance. The more people you have, the easier it is to claim that something is unexpected, to be out in the tails in terms of that. But the thing that's out in the tails is the effect size. So the strength of a relationship is an effect size. So for instance, R is an effect size. D for a standardized mean difference is an effect size. It's an absolute way of describing the size of a relationship in a standardized metric or something that's close to standardized. The sample size, if you have a larger sample size, that does not mean that you are going to have a larger effect size. Those two are separate. But sample size does relate to effect size in the sense that it is related to the variability of the effect size. So this is a tricky concept. I wanted to pull up a picture from lecture 2. So this is from before when we were talking about power, to try and remind us of that idea. So this picture here that's highlighted, this is me drawing repeated samples from a population where two variables are supposed to be correlated 0.3. And these histograms show for different sample sizes within each of the repeated draws what the correlation was within each of the sample. And so this is the distribution of the obtained correlation across repeated samples of the same size. And so the point that I wanted to make here is that at size 42, there's a lot more variability in what that correlation ended up being in any one sample, even though I know the right answer is 0.3. All of these samples came from a population where the correlation is 0.3. But what you happen to get in any one set of 42 people is a lot noisier than what you would happen to get in any one sample of 85 people. So the more people that you have, the more precise your estimate of effect size is going to be, the less variability you would have across repeated samples. So from that perspective, Jerome, you are right that sample size is related to effect size, but it's not related to the amount, it's related to its variability. That's what I would say. And so then that idea of more variability is what constrains statistical power, your probability of detecting an effect that is present as statistically significant. And so the line in the sand here, the cutoff, these are t-test statistics then that were derived from these correlations. The proportion of replications in which t cross the threshold for significance is shown in each of these graphs, and that's statistical power. So you have more power in a sample size of 85 to say that a correlation of 0.3 is different than 0. So your likelihood of finding significance is a function of effect size and sample size, but it's easier to find it if either is bigger. And it's a nonlinear function for both of those things. And as several of you pointed out, the fact that sample size is related to significance is why it's important to always give some measure of effect size in addition to just your p-value, because that helps to clarify or, what's the word I want? Contextualize what you found. How big of a relationship is it? How big of a difference? Just that it's significant could mean that you have 8 million people. And the same is true of the opposite. If you only have 40 people, you don't have very good power in finding a relationship to be significant. So knowing that the correlation is 0.3 is informative in and of itself. Knowing whether or not your particular correlation is significant in a sample is a function of sample size. Okay, Does that make sense? Yes? Okay. Good. And so the instances in which you have very low power to detect an effect, but yet it happened to pop up significant in any one sample, those are instances in which you would have a concern about replicability. You could have just gotten lucky, essentially. All right, I think I can put that away. And that's the last question. So anything you want to talk about anymore, or again, or differently related to these ideas? No?
Can
Yes?
I ask a question, Lisa?
Please do.
So from like a paper publishing perspective, so do you recommend that we put like both the effect size as well as the significance test in our report? Okay.
Absolutely. Generally speaking, for every relationship that you want to talk about, you would have some kind of unstandardized estimate, so like a slope value, the standard error that goes with it. If you have those two things, that is sufficient to generate a t-test statistic, a p-value, and a confidence interval. So really, it's the estimate and the standard error that are like the meat of the sandwich that you have to have. The rest of it is sort of optional. But then converting that slope into some kind of an effect size would be like the third column that's mandatory. And so there's different ways of doing that. And there are different ways that are more or less common in various types of fields and with data. So for instance, in medicine, you'll see odds ratios used as effect sizes because they're often predicting categorical or binary outcomes like mortality or disease presence or something, and odds ratios are effect sizes that go with that as a prediction of a binary outcome. If you have group differences, something in the D family for standardized mean differences would be more common. If you're talking about relationships of quantitative variables, something that's R or eta square or something like that would be more useful. So just giving them something is the best thing to do. And more common is journals requesting supplemental materials where you give them like literally syntax and output and things that are much more replicable, so to speak, not just your summary of the information, but making everything available to the reader in an online format is becoming more requested, I would say.
And the reviewer would understand my naming convention, my calculations. They are expected to do that.
Yeah. I had to build like a supplemental materials thing to address reviewer comments that was almost as long as the manuscript for a paper that just came out this past year. No, and then they'll probably like, can you annotate your code for us? Like, fine, but yes. In all seriousness, the more transparent you can be about what you did and how you did it, the better cited your paper is going to be. And not just for the conclusions that you're going to draw, but also the methodology. Like, I followed the approach in Hoffman et al., right? Like, because they have the syntax, they have the results, they have the syntax, it becomes much more doable from a novice perspective. So it's actually a good thing, even if it is somewhat of a pain in the ass. So, yay, science. All right, any other questions on this before we change gears? Or anything else you want to talk about? Sources of confusion or lingering doubt?
So I'm not afraid to look stupid in front of everyone, so
Good.
I'm just going to ask. So initially, I said something about degrees of freedom and effect size. I don't know, and that wasn't correct. And I didn't look at anything when I answered that, but would there have been a logical reason I thought that, or am I completely off base?
I think it's logical from the perspective that the primary ingredient in degrees of freedom denominator is sample size. So higher degrees of freedom is a proxy for more people. But degrees of freedom also reflects the complexity of your model because you're keeping track of how many slopes it took to get to a certain level of R square. So it's both. But that may have been where you were going with degrees of freedom. That's my guess anyway.
Gotcha. All right. Thank you.
Sure. All right. Then we've got some new stuff to talk about here. get back to the beach. So moderation is the topic for the last 3 weeks here. Probably maybe not starting today or not getting very far, because the first thing that I want to go over is ways of making your results understandable. So the idea of being able to make figures for posters, for talks, for papers is a very useful thing to do, and it's not necessarily something that you would get taught. And so I wanted to at least give you some resources to get you started in that. And then the situation in which figures are going to be most useful is when you have models that include moderation terms. So that's sort of the necessary precursor. So we're going to talk about all this different kinds of stuff in this unit. So let me, away we go. So if you want to make a figure that shows the results of your general linear model, here are 3 different ways that I can think of in order of most to least painful by which you could do this. So in number 1, something that I do frequently for pedagogical purposes, and I also do it for transparency when I'm working with other co-authors who may not understand SAS or Stata code, is to make predicted values to illustrate what your model is doing using Excel. So I'll show you what this looks like, but basically you would hand enter the coefficients for your intercepts and slopes. You would hand enter prototypical values for the predictors in your model, and you would write a formula that creates a predicted outcome for each case. So this is good from like a mechanical, do I understand what the model's doing kind of perspective. It gets annoying quick, and hand entry of anything is more likely to cause errors. The other piece of it is that you then do not automatically get a standard error that goes with your prediction. So a lot of times when you make a figure, people want you to have error bars around a point to show its expected inconsistency, and those you'd have to calculate too. There are formulas for them, but it's just a little more mathy. Number 2 is something that you'll get a chance to practice in you've actually already done this throughout the semester. We started doing this in homework 3, and you'll get a chance to practice it some more in the last homework 6. Programming statements. So if you know how to ask for it, any software program will happily spit out predicted values for your outcomes that are drawn from the model you estimated. So these are estimate statements in SAS. For instance, you had to create the predicted number of fits thrown for a 3-year-old and for a 4-year-old and for someone who says please like 10 times. Do you remember doing that? And you had to create the predicted golf score for people who got training in mini golf and that kind of thing. Those sorts of predictions is what I'm talking about. So you have some exposure to this already. So it's estimate in SAS. It is lincom or margins in Stata. And I'm learning in R, there's various different ways to do this. There's EM means and LS means and contest 1D and GLHT and all kinds of things. SPSS, by the way, can do this using a test statement in certain packages, but not all of them. So this is better. It is more time consuming to write the code, but then if you change the model, all you have to do is rerun it and all of your information is repopulated and becomes current. It also gives you standard errors for anything that you're asking for. And finally, the way that I tend to do it when I'm cranking analyses in my life is what I call the method of fake people. This is going to sound crazy, but just bear with me. You make up fake people and add them to your data set who have the prototypical values of the predictors that you want to put in your plot. You make up the cases, you add them to your data, you re-estimate your model, adding in a line of syntax that says, oh, can you generate a column of predicted outcomes for everyone in my data file? Okay, thanks, bye. And it does so for all of your real people, and it does so for your fake people too. And so then, no matter how complicated your model is, you have a set of correct predictions that you can then plot directly within your program, or you can bring into a different program if you want to make pictures a different way. So the reason that this is not crazy is because when you're making these fake people, you don't give them an outcome. You only make up values for their predictors. And so they don't mess anything up when it comes to estimating the model, but they do get predicted values along with the real cases. So those are the three things that I wanted to show you, in particular the last two, since that's code-based. Okay, am I frozen? No, am I boring? Never. Stats class is never boring, especially not right after lunch. Definitely not. Although, if we had to take a vote, who'd rather be here at 8 a.m. versus 12:30? I still think 12:30 is like the least of the evils, right? All right. So here's a quick depiction of what the first option would be using Excel. So this is based on the ending model in example 5B, which is the videos I posted for last week, and is going to be the starting model for example 6. So I would enter the estimates standard error, the estimates for the solution. I would enter values for my predictors. So for instance, this is a model that has age that's centered at 85, grip strength that's centered at 9, and we're predicting a cognition outcome, and these are samples of older adults. We also have a value for their gender and a value for whether or not they are a member of each dementia group. So we'll talk more about what the variables mean in the example, but just know that those are what they are. And so what I'm doing here is selecting people who are relatively young on age as my prototypes, average or above average. So 75, 80, 85. I did the same thing with grip strength using plus or minus 3 because that was approximately the standard deviation of this variable. It's in pounds per square inch. And so then I have a column out here, number 3, which is the y hat. So the predicted outcome using these coefficients over here in step 1 combined with these values for the predictors that show what the expected outcome looks like for people of different levels of strength and people of different ages. I then have to reconfigure this column of 9 values into the 3x3 table that it actually corresponds to in terms of low, medium, high for each of these 2 dimensions, and then ask Excel, for instance, to make a line graph displaying these numbers, and then this is what it looks like when I'm all done. So have you done something like this before in your lives? Do predicted values to make pictures? Do you just not make pictures? Is that the trick? Jen's like, yep. I don't make pictures. Well, at some point in your life, you will need to make pictures. I can guarantee it. So this is the process that is somewhat transparent and useful for pedagogical reasons. It gets annoying quickly in practice, and it's error prone. Because anytime you have a human in between, the information, entering values, no matter how careful you are, you can still screw it up. So this is that. Here is the exact same thing using SAS, and I'll show you Stata in just a second. So here's the model. ProcGLM, the outcome for this set of examples is going to be a measure of cognition. So it's going to be a crystallized intelligence. And we have age, grip strength as a proxy for physical function. We have a binary gender, and then we have a 3-category dementia variable, and here are the 2 dummy codes that will go with that. And I have estimates that give me the same 9 predictions that I calculated manually in Excel. So these numbers that correspond behind each of the variables are the multipliers of the betas. So intercept 1, if I type this here, what am I actually telling SAS to use? What does SAS do when I type intercept? What is that referring to? Do you remember? Don't remember? I'm a Stata guy. Okay, so if you type const instead, I'll show you that in just a second. Either way, if you type constant in Stata instead of intercept, same deal. What's it doing?
Is it referring to the intercept of the model?
the beta 0 estimated intercept, exactly. It's what the fixed intercept is going to be. The word intercept or constant in Stata is a placeholder for that idea. Likewise, if I have age 85 as my first predictor here, that does not refer to the variable. It refers to the beta associated with that variable, the slope. So beta 1 in that case is right, Jerome. The number refers to the value of the variable that goes with it then, the multiplier of the slope. And so then I'm filling in what the prototypical values I want predicted for each of these cases. And so I'm varying age and grip as just described, and I'm holding constant the other variables so that they are specific to whoever the 0 group is for these. And I end up with this table of estimates. I can then save this table, turn this set of labels into variables. So I have some code to do that here, where I'm carving up the label into variables for age and grip. And then sgplot is a command in SAS that you can make pictures with. And so this is the SAS version of the same picture that I made in Excel. That's not so bad. So those of you who are working in Stata, who's working in Stata this semester? I know Jen is. Anyone else? Okay, yes, EPLS people, you need to pledge allegiance to Stata. They will kick you out otherwise, I think. No, I'm just kidding. But yes, they're very big in the Stata field. You're going to love this. All of it in way less code. So margins is magic. I don't know of anything in SAS that is analogous to this, and this alone would make me want to use Stata if for no other reason. So the way that this code works is is how you tell it what the values of the predictors are. And rather than having to write out every specific combination of predictor values, you can give it ranges. So the key to understanding what this little sequence here, this -555 is it goes from, in increments by, and then ends at. So from and to. So what this is saying is, hey, can you start at -5, go in increments of 5, up to 5? So that generates all combinations of -5, 0, and 5. Oh, and do the same thing for grip strength. Start at -3 in increments of 3 up to 3. That gets me -3, 0, and 3. And it knows to do all possible combinations. And then I'm holding the other covariates constant at 0. So just the margins part generates a table of predicted values. Then it's like, oh, hey, did you want a picture? Sure, I'll stick that table in a margins plot. And you tell it which dimension you want as your x-axis, and there it goes. So this is pretty slick. And a window pops up that has this in it that you can then, there's a graphical interface that you can customize the legends and the axes and stuff like that. I imagine that can be done in code, although I've never bothered to learn how. So this is a very efficient way of doing all of this. And here's option 3, the fake people. So I'm demonstrating this in SAS only because Stata doesn't really need this. But I would create a data set that I'm calling fake people. I tell it what columns I want in the data set, and I can then tell it to center the predictors as they are in the data. And then I enter these lines of data into my data set. So it's the same combination of low and medium and high for age and grip strength. I am giving these fake cases all an ID number of -99 so that when I sort, they'll appear first. That will make it easier to go and find them. I merge these fake data in with the real data, and then the key is that this right here, this output out, that generates a new data set that has a column for y hat, which is this predicted option here, as well as its standard error. And so then I can take the 9 predicted values and their standard errors, and I can go stick them in a plot, which works out to be the same thing as this right here. Okay. There, that's all I wanted to say about that for a moment. How are we doing so far? So here's a question. What is this plot telling me? So the x-axis in this picture here is grip strength. How does this picture tell me grip strength appears to relate to predicted cognition? Here, I'm going to go to the SAS one because the labels are better. If
There's
I,
like a positive linear relationship.
yeah, so people who are stronger do better on this test. What does this plot tell me about the effect of age? Which is the differences between the lines. So blue at the top is age 80, red is age 85, and green is age 90.
Is a similar. Oh, sorry, everybody else. Yeah, there's similar effects, not really related to age.
Similar effects.
Similar, since the slope is the same, so it'd be similar, like prediction.
Well, the slope actually refers to the effect of grip strength. The distances between the lines refer to the effect of age. But I think you're getting at something which is foreshadowing where I'm going with this. The idea that they're parallel is also meaningful. But in this case, the predicted values are highest for the 80-year-olds and they're lowest for the 90-year-olds. So does age have a positive slope in predicting cognition or a negative slope? Yeah, negative, yeah. The younger you are, the better you do on this test. The older you are, the worse you do on this test. Getting old is bad for you. I wouldn't recommend it. Actually, to be fair, getting sick is bad for you. As someone who used to study cognitive aging, that was a major point of contention, is that aging is not bad for you. It's all of the things that happen to older adults in terms of failure of their various systems that's bad for you. If you're healthy, you can live forever. But I think where you were going with this, Emmy, is that these lines are parallel, right? So what does that imply about the effects of these two variables?
Yeah, parallel was the word I could not think of. So trajectory is kind of what I'm thinking. Like, yeah, I don't know what other words I can't think of, but parallel was what I was trying to say.
Mm-hmm. Is it a coincidence that these lines are parallel or a consequence of the model?
Seems like a consequence so far, as opposed to a coincidence.
Yeah, it is a consequence of the model. Because this model, so we have, I'll show it to you in, this is the beginning of example 6 here. Let me fast forward through the data manipulation steps here for just a moment to look at the model. This is the model that generated that picture. That model is consistent with the idea of parallel lines because this model specifies that age has an effect and grip has an effect, and that's it. There is no interaction between those two variables. The effect of age is thought to be the same for everybody in the sample, and the effect of grip strength is thought to be the same for everybody in the sample. And so that type of model, which is now, I'm going to switch terminology on you. So these are no longer just slopes in this model. These are main effects. Am I frozen again? Because y'all looking like I have frozen face. Like the same level of like, ugh, on everyone at once. Maybe it's just a coincidence. Hopefully not a consequence. I'm trying here. I really am. We have week 13 face. Yes. Yes, but I am going to fake it through. We are going to be enthusiastic. Damn it. This is what's going to happen. Why does this thing keep like showing up? Anywho. So the fact that each of these predictors has its own effect, and that effect is supposed to operate equally on everybody in the sample, these slopes are now going to be called main effects, meaning that they are marginal. They apply to everybody. So beta 1, for instance, in this equation is the effect of a 1 unit difference in age on the outcome for everybody. Main, marginal. Once we have an expanded model, we'll have different kinds of slopes that are going to be called interactions instead of main effects. So that's where we're headed. All right. So yeah.
Was the word that you said marginal? The audio cut out a little bit.
Yes.
Sure. Okay.
Yes. So the idea is that in that equation, each beta is a constant, not a variable. And it applies equally to all the cases in the data set. So I would think of it as unconditional, as marginal, as a main effect. That's going to change when we add new terms to the model that represent interactions by which to test moderation. Okay. Other questions or clarifications? All right, so we're going to do this then. Welcome to moderations. So this is slide 8 of lecture 6 that we're on. And we're introducing a new type of slope here, highlighted in the green box. So we have, in this example, we're sticking with just generic variables for the time being. I have y as my outcome. And why do I have an I subscript here? Quick review. What does little I subscript tell me?
Individual.
Yeah, each individual has one, meaning it is a variable. And so the same is true of x and z and the two of them in combination. So these are variables that are measured in your data set. So x is going to be one predictor, z is going to be a second predictor. Our friend E sub I here is still, what do I call this thing?
Residual?
Yeah, residual. Or error. I'll take that. I don't like that one as much, but that's why it's E. Some people turn this into an R for residual to make it explicit, but whatever. This is consistent with all the rest of my notation in my other classes. E is how far off your outcome is from the one that's predicted by the model. So it represents unexplained deviations for each individual. But here's the new thing here. So x and z together as a new variable. And it has a new slope attached. So beta 3 is what's known more generally as an interaction term. You have seen a special case of interaction terms earlier this semester when we had a quadratic effect, because it was like age times age, and in your homework it was enthusiasm times enthusiasm. Well, the same is true here, it's just it's not the same variable multiplied by itself, it's two different variables. So it changes how we think about the model specifying, okay, what is the effect of x? This model says the effect of x depends on what you have for z. And it also says that the effect of z depends on what you have for x. So it's asking if the relationships between the predictors and the outcome differ for different kinds of people. That's the idea of moderation. So typically speaking, when people phrase hypotheses about moderation, they're usually phrased as one variable being the predictor and the other being the moderator. But that is a substantive decision, not a mathematical one, because these interaction terms do two things at once. They manipulate the effect of one variable, the slope for one variable, as a function of the other, and it goes in both directions. So we can always test interactions between variables no matter what kind of variables they are. Meaning whether it's a quantitative predictor, a categorical predictor, an ordinal predictor, whatever, if you have a hypothesis that the effect of one predictor varies as a function of something else, you can phrase that no matter what kind of predictor variables they are. However, one of the reasons why I make a point of putting this unit in this class is because it is so foundational for so many other things, and because it's historically taught very differently depending on which silo of the general linear model you find yourself in. So for instance, if you are doing ANOVA, you may have multiple factors. So if you have a condition that has 2 levels and another condition that has 3 levels, for instance, that would be called a 2-way ANOVA. So I know, Fayaz, you had design of experiments, right? This should sound familiar from that perspective. In that context, when you have multiple categorical predictors and you do ANOVA, by default, it includes all possible interactions between them. So if I had a 2 by 2 by 2 by 2 by 2 design with like 5 different factors, the default model, like when you pop this into SPSS, is a 5-way interaction, all possible 4-way interactions, all possible 3-way interactions, all possible 2-way interactions, and all main effects. And that's your model. And it's insanity. But that's like not questioned. And unlike any other model, typically people don't prune it, remove non-significant things, and simplify. It's just left as this gigantic thing. If you were doing ANCOVA, let's say that you have the same 2 by 2 by 2 by 2 by 2 5-way design, and you want to control for age as a covariate. Then, curiously enough, age does not get included in any interactions. It just hangs out as a main effect. Well, why wouldn't it go to be a 6-way interaction? I don't know. I didn't make the rules. This is just what happens. There is actually an assumption that goes with that specification that the effective age would be the same for all different kinds of people, that the effective age shouldn't interact with any other factors. And that's a testable hypothesis. It's just then it wouldn't be called ANCOVA. But then if you take a class in regression, you don't have interaction terms by default. It is totally up to you which ones you should include and in what combinations. And in most regression specific packages, you have to literally make the new variable yourself. In most standard regression packages, you would have to compute a new variable in your data set that is a column of x multiplied by z, and that would become a new predictor. We avoid this by using GLM and regress because we can define interaction terms on the fly in those packages. But this is craziness as to whether or not interaction should be included by default as a function of what kind of predictor. No. Interactions should be included if they answer research questions or if they're plausible in terms of just the content of the variables. So it is probably more often the case than not that the effect of a predictor is different for different kinds of people. And so having the flexibility to be able to specify those sorts of interaction terms amongst any kind of predictors is going to be very helpful to you. So have any of you had coursework along these lines before? Does this sound familiar at all? Fayaz, a little bit? Yeah?
So did you say that like in order to get the interaction term, we needed to multiply the variables manually?
In some regression software.
In R, you could just use the asterisk and it would do it. Yeah.
In R, it's a colon, I think. In Stata, it's a hashtag, and in SAS, it's a star. But in, like, if you do regression in SPSS, or if you do proc-reg in SAS that's regression specific, you have to make the new columns. The same is true in M+, by the way. So yeah, it's an older sort of convention that most modern packages can get around. So in terms of rules of engagement here, anytime that you specify an interaction slope between two predictors, you have to keep the main effect slopes in the same model. So I know I'm introducing some new terminology here. The idea then is that, like, if I fit this model right here with this beta 3, in order to have x and z in combination as the interaction term, I have to keep each of their contributions by themselves. So the contributions by themselves are what we call main effects. So beta 1 is the main effect slope of x, beta 2 is the main effect slope of z, and beta 3 is the interaction slope of x by z. So you'll hear me start to switch into this language of main effects, but just know that it's still a slope. It's just a new label for how to think about what the slope means. So we have to keep the main effects. That's number one. And the good news is that even though this may look a little bit complicated, it's actually not. It's incredibly algorithmic. And once you know how to approach the problem, it becomes very straightforward in how to solve it. The key is just learning that approach sequence. And the good news is that there's only 4 kinds of interactions in the world. Only 4. So when you approach a set of analyses and you get your results, it's just you got to figure out which of the 4 it is, and then you're home free. And the direction of the coefficients tell you that directly. The catch then is making sure we know what to do with the main effect slopes, because their interpretation changes once the interaction term is in the model. So this is a different level of conditionality than what we have had up to this point. So I wanted to try and introduce a taxonomy of language that may help in explaining the distinctions a little bit better. So at the beginning of the world of general linear models, we had these 2 terms. We had an intercept and we had a slope. So these 2 terms more generally in these models are known as fixed effects, where the term fixed means that they are estimated constants. So we have an intercept that tells us the expected outcome when our predictors are 0, and we had a slope that tells us what the change in y is for a 1 unit change in x. Cool. That was clear. Now we have to decide whether or not a given slope in the context of the model should be interpreted as a bivariate marginal effect, a unique marginal effect, or a unique conditional effect. So this same idea of a slope meaning the change in y for a 1 unit change in x has an additional layer of interpretation put on it based on the context of the model. So what do I mean by these? So if you're in a model where there is only one fixed slope, it's bivariate, and because there's nothing else in the model, it has to be marginal. So if I have one predictor in the model, that beta 1 for that predictor is its effect for everyone across all persons. It's a constant. That's what marginal means. If I have models with more than one predictor simultaneously, so we talked about this earlier. If I have more than one predictor simultaneously, each of those slopes becomes a unique effect, controlling for the contributions of all the other variables. What does that predictor bring to the table that the others don't have? What room did that person clean that the others in the family didn't claim they cleaned also? And so that idea of controlling refers to unique effect, but in the models we've seen up to this point, it's a marginal unique effect. Like it's the effect of age for everybody. It's the effect of grip strength for everybody. The new layer that we're adopting is unique conditional, which means that a given slope is interpreted not only as a unique effect after controlling for the other predictors, but specific to a value of the interacting predictor, the 0 value in particular. That is the hardest part because the model implies an infinite number of potential slopes when you have an interaction term. The one that you get on the output just happens to be one of them. So what do I mean by this? You want to practice with me? Are we willing to do a little play along? Love to. Thank you. I don't care if the enthusiasm is real. It's week 13, folks. I'll take whatever I can get. Do you want me to type with you? Would that be helpful? Yeah? That means I have to exit out of the slideshow here and get back to that slide, of course. Here we go. I'll type with you. Let me hide this thingy again. Okay. So each of these here, you've got three choices. Each of these slopes is bivariate marginal, unique marginal, or unique conditional. So I'll zero in on here. First model. If this is my model, which of those three labels do I use to refer to beta 1? We got one vote for the first one, bivariate marginal. Another vote for the first one. Yep. And how did you know that? Because that is correct.
There's only one predictor.
Yeah, it has to be bivariate if there's no competition involved. And if it's bivariate, it has to be marginal. So it is, in fact, bivariate marginal. And I'm putting in parentheses here, beta 1 applies to all. So that's what the marginal part means. Now if we have something a little more complicated. So I have a slope for W, I have a slope for X, a slope for Z, and now this thing, an interaction slope for their combination of X and Z. So now, how do I talk about the beta 1 slope for W? Bivariate marginal, unique marginal, or unique conditional? Okay. Got one vote for 2. I'll help you narrow it down. It can't possibly be bivariate with all this stuff in the model. So is it unique marginal or unique conditional is the catch? Well, we got several votes for 2. The 2s have it, yes. And the reason that I know that is because W is only right here. There's no other terms in the model that talk about what the effect of W should be. So beta 1 is the slope for everyone. It's a, unique marginal time. Can't type and talk at the same time, I have learned. I also cannot do math while I'm teaching. So it's not a coincidence that I have all of this stuff prepared ahead of time. But it is unique marginal because it is after controlling. That's what the unique part is. And the marginal part is for all. Okay. With me so far? Now this one. Beta 2 for the slope of X. Yeah, it can't be bivariate, so that I'll rule that one out. It's either conditional or marginal. Yeah, this is the conditional one. Unique conditional, because it is after controlling, but it's not for all. It is specifically for Z equal 0. That's the conditional part. Now, where did that come from? If I am a person who has 0 for my value of Z, what happens to this last term here? If Z is 0, yep, it gets canceled out because 0 times anything is 0. So that is the only circumstance in which the effect of X is given by beta 2 and beta 2 alone. Therefore, that is what beta 2 means. It is the slope for a 1 unit change in X, specifically for a person with a Z value of 0. So that could be someone in the reference group. If Z were a grouping variable, that could be conditional on 0 for a quantitative variable, but 0 is the key. Similarly, what goes here for the effect of Z? I got one vote for 3. Another vote for 3. Yep, this one is the same idea. So I'm going to cheat and copy. Unique conditional. because it's after controlling. That's the unique part. And the conditional, what do I need to change to make this correct? If I'm talking about the slope of z, it is conditional on what?
Changing z to x.
That's right. Same idea as before. The only situation in which beta 3 gives me the full effect of z is if this last term gets zeroed out, and the only way that happens is if x goes to 0. So you can't just look at, say, this beta 2 or this beta 3 to answer the question, does x matter? Does x relate to my outcome? Because they only tell you about how that predictor relates to the outcome for a particular kind of person. The interaction term tells you how that relationship changes as a function of the other interacting predictor. Okay. Questions? No. Do we have the strength for one more? Okay, this is a tricky one maybe, or maybe not. The interaction term. I'll give you the same hint. It can't be bivariate with all that stuff in the model. Yeah, we got 2 votes for 2 for marginal. Another vote. We got some hesitant votes. That's like ish, 2-ish. Can I just say 2.5? Does that fall? It is 2. It is unique marginal. Now, what made you decide to pick that answer?
Yeah.
When you're
Fair
looking
enough.
at both, when you're looking at both x and z, there's no other term that has both x and z.
Exactly. Like x and z together is like a new idea. And there's no other term in the model that also has both x and z. So beta 4 describes the interaction for everybody. So I'll put that in parentheses here, for all. So beta 4 moderates the effect of x as a function of z the same way for everybody. Who knew there'd be so many words, right? People say that, stats is math, but it's not. There's a lot of language in here. And a lot of terminology that is accepted and used without necessarily ever having been introduced. So I wanted to be the one to help with that. So this is the way that I think about these things. In any given model, the context of the model tells you how to interpret that slope and how to think about it. The good news, here's another fill in the blank one, is that there's only 4 kinds of interactions in the world. That's it. The role of an interaction is to take the main effect of each of its predictors and to either make it more positive, less positive, more negative, or less negative. That's it. It's the same 4 kinds of quadratics that we talked about a couple weeks ago. So same model here. Help me fill this in. If I'm focusing on the slope of x, so this is my predictor, and I'm thinking about z as a moderating variable. So if beta 2 for the slope of x is 10, let's just say, making some numbers up here, and beta 4 for the interaction term is 2, then what does the model say is going to happen to the slope of x as a function of z, if these are my numbers? If the slope of x is positive and the interaction term is positive,
More positive?
yep, this is more positive. More specifically, what this would say is that in this first line here, beta 2 is 10. So y would be predicted to go up by 10 for every unit change in x for somebody with a z of 0. If beta 4, the interaction term, is 2, what that is saying is that beta 2 becomes more positive by 2 for every unit higher in z. So it's a strengthening. Conceptually, it means that the effect of x is stronger in people who have high z values than in people who have low z values. It would be a strengthening, a magnification of the effect. If I had the same positive slope of x, that's 10, but the interaction term beta 4 went negative, then what is z doing to the effect of x?
The slope of z is negative.
The interaction term is negative. The slope of z by itself is irrelevant because we're treating z as the moderator in this story. But we had a guess for less positive. That is correct. So what's happening then is that same story at the beginning. Beta 2 is 10, but beta 2 becomes less positive by 2 for every unit higher z. So this is the opposite trend. The effect of x is less positive, is weaker in people who are higher in z, if these are my coefficients. So it's a dampening. How about this combination in the third row, where they're both negative? If my beta 2 slope is minus 10, and my beta 4 interaction slope is minus 2, what's happening as z increases? Yep, this is more negative. So the effect of x is stronger in people who are higher on z. So both this first pattern in the row here, in row 1 here, and the pattern in row 3, those are both what are known as over additive interactions, where the effect of a predictor is stronger the higher you are on something else. And that means the last one here, what's left? Yeah, this one's less negative. So this is the same pattern as in row 2 of a diminishing. That's an under additive interaction term. So it becomes, the effect of a variable becomes less helpful, less strong, weaker. I'm running out of English too. It goes down less negative. So all you have to do is look at the pattern of the coefficients and you'll know how to talk about it. There's only 4 kinds. It's highly algorithmic. So I'll show you a little more math as to how you can ask for what the model implied effect is at any of these predictors here in a minute, but I just want to get the concept here of what's happening. You're saying that the relationship between, in this example, x and y is either getting stronger as a function of a third variable or weaker as a function of a third variable. And you have to know the signs of the main effect slope, so the slope of x, beta 2 in this case, and the interaction slope to determine which of these 4 patterns it is. So terms that you may have heard in your research. Have you heard of something called a risk factor? No? No? Okay, fair enough. I'm trying to think of other euphemisms for this sort of idea. Not in research, at least. Touche. the idea of protective factors. So a protective factor is a moderator that takes a negative effect and makes it less negative. So do you think stress is bad for your health? Can we all agree on that? Stress is not helpful. Stress would have a negative effect on health. And people who are trying to cope with stress, they are suggested to do what? We've all gotten invitations to 8,000 Zoom seminars about how to deal with our pandemic stress. The great irony, of course, is that how do you deal with Zoom fatigue? With another Zoom meeting focused on Zoom fatigue. But they're full of helpful suggestions, right? Get more sleep. Go for a walk. Reach out to a loved one. Spend time with your partner or your children or your dog, right? There's all these like things that you can do. Like these are protective factors that are supposed to dampen the negative impact of stress. Are video games bad for you, Fayaz? No. Would they be potentially more bad in children who are neglected?
Yeah, because of maybe social reasons, because they won't get the nurture that is required, the scaffolding and the support of more capable family members.
Yeah. So there are situations in which the effect of something can be made worse by related factors, right? That's the more negative or the more positive idea. So a lot of social science research uses these sorts of terminology. They're talking about moderation. That's what they're talking about. Dampening of predictor slopes or enhancements of predictor slopes. All right. Thoughts, questions? Circular reasoning? Which part's circular?
Well, that was in relation to the stress stuff, or just talks in circles. But no, I was gonna say the slope and interaction things make sense. Like if your slope's positive, you'll be positive in some way. If the coefficient or the interaction is also positive, you're more positive, and then just the inverse for the negative stuff. So that's gonna stick in the old noggin there. So.
Well, here's a real life example that a student came up with last semester. He had a research hypothesis that turning your camera on would be related to good grades, but only in small classes. That was the hypothesis. Small class. Jerome says, yeah, no, wait for it though. Because then it's like, well, what are the factors that might cause a student to not have their camera on that have nothing to do with their motivation to succeed and participate? Maybe you have screaming babies in the background. Maybe you have other people hammering on your roof. Maybe your internet is not strong enough to permit you to have your camera on consistently, right? There's all these things that should go into the model also as like the W here. All the other covariates that would be related to camera use that hopefully then would make the effective camera use more just that and not other things that are correlated with it. But that idea that camera use should relate to grades only in small classes, that's an interaction term. So, yep, camera use matters more if your class size is smaller. That's what it would be phrased as.
One of my professors shared a finding from a paper, I don't remember the name, but it showed that it's more stressful if students turn on their camera and keep them turned on.
I believe it. I believe it was Solomon, Jen. Do you know him? I think that is who mentioned that. So yeah, that's I appreciate cameras being on, but I'm also realistic that it's weird. This whole thing is just weird. So we all get through the best way we can. And it's not always possible to have your cameras on or advisable. So anyway, I'm off topic. Interaction terms, very prevalent in research, make sense in real life too. Because the answer to whether something is good for you or bad for you is almost always, well, it depends. And that's the idea that is being gotten at in this model. All right, today was garbage day. That means I don't say have a good weekend. That means I say thanks for joining us. See you Thursday. You're able to work on all of your next homework, so let me know if you need any help with that. Otherwise, I'll see you later. So, peace out, everybody. Thank you.